Hi, this is Justin Fowler, and this is my presentation on ATP pathways for advanced exercise physiology for Cal Baptist University. So let's quickly talk about ATP. ATP is adenosine triphosphate. It's a high energy molecule found in every cell and is often referred to as the energy currency of life. Energy from the oxidation of macronutrients, proteins to a limited degree, carbohydrates, and fat, they're all harvested and funneled through energy-rich compound ATP. When an ATP molecule is combined with water through hydrolysis and acted on by the enzyme ATPase, the last phosphate in the group splits away and releases a large amount of free energy, converting ATP to adenosine diphosphate, meaning 2. We can see that diagram here in the middle of the page. This energy from ATP is then responsible for powering bodily functions like muscle contractions, etc. Cells generate ATP through one or a combination of 3 metabolic pathways: the ATP-PCR system, the glycolytic system through glycolysis, and the oxidative system through oxidative phosphorylation. Let's look at some pictures really quick in dealing with these 3 systems. So on the top left, we have a picture of a book of matches. We have a limited amount of matches in the match book here, but we know when we light the match, it's going to quickly provide energy, but it's going to burn out fast. May give us 5-10 seconds worth of energy. This is very similar to the ATP-PCR system. Our ATP-PCR system is going to provide us quick energy, but it's going to burn out fast, maybe up to 10 seconds of maximal effort. The energy then from ATP resynthesis must come from stored macronutrients, which would be our carbohydrates and palmitate primarily. The next picture is a picture of a group of papers. So once I take the match that is burning and I set it on a group of papers in the fire pit, both the match is going to finish burning out and the papers are going to burn at the same time. So there's a little bit of a transition there. The papers themselves are going to be readily available and they're going to burn, but they're going to burn out fairly fast as well, maybe within a couple minutes. And this is very similar to our carbohydrates or glucose. Those are going to be readily available, but they're going to burn out fairly fast. Once I have my papers burning, I'm then going to take my wood and put my wood on top in the fire pit. And once I do that, it's going to take longer for the wood to start burning or be made into usable energy. But once it starts going, it's going to burn considerably longer than the papers and the matches. This is very similar to fat or the palmitate. It kind of gives you an idea of the 3 energy systems. Let's specifically talk about glucose and palmitate. So let's talk about ATP production from one molecule of glucose. Glucose itself is a 6-carbon molecule. And to start this process, we have an energy investment of 2 ATP. Glucose will go through glycolysis, in which the 6-carbon molecule of glucose will be divided basically into 2 3-carbon pyruvates. Through this process of glycolysis, we have 4 total ATP produced. However, remember, we utilized for the investment 2 ATP. So we have a net gain of 2 ATP on the left-hand side here. And this is all occurring within the cytoplasm. Not only do we have the 2 pyruvate created, we also have 2 reduced enzymes of NADH created as well. And those are going to make their way to the electron transport chain. Through oxidation, those 2 pyruvate, 3-carbon pyruvates, are going to make their way or become 2 acetyl-CoAs. And the acetyl-CoAs each are going to lose a carbon. And that kind of leaves our system in the form of carbon dioxide. This acetyl-CoAs, or these 2 acetyl-CoAs, well, back up for a second. This oxidation process is going to also create two reduced enzymes of NADH that make their way to the electron transport chain. But the acetyl-CoAs themselves are going to make their way to the Krebs cycle. The Krebs cycle is going to turn twice. Oxygen must be present within the system, and within the system there's also GTP, which is easily converted to 2 more ATP. This occurs in the mitochondria, and if we add our 2 ATP from glycolysis to our 2 ATP already created from the Krebs cycle, we end up with a subtotal of 4 ATP. Krebs cycle also produces, in its 2 turns, 6 more NADH and 2 FADH2, which is another reduced enzyme. These all head to the electron transport chain, and a conversion takes place. The current thought on conversion rate is the following. For every 1 NADH, it is 2.5 ATPs, and for every 1 FADH2 is 1.5 ATPs. So we have to multiply our calculations here. So 2 NADH multiplied by the 2.5 provide us 5 ATP from glycolysis. From oxidation, the 2 NADH provide us another 5 ATP, and the 6 NADH from the Krebs cycle provide us 15 ATP. The 2 FADH2 from the Krebs cycle provide us 3. So it was 2 multiplied by the 1.5, providing us 3 ATP. This all adds up to 28 ATP and another subtotal. So we add our subtotals together and we come up with 32 ATP. So there's 32 ATP produced from 1 molecule of glucose. Let's look at the yield here of 1 glucose molecule and ATP produced, just in a quick review. So the 2 ATP from glycolysis gave us 2 ATP. The 2 NADH from glycolysis provided us 5 ATP. The 2 NADH from pyruvate oxidation provided us 5 ATP. The 2 GTP produced in the Krebs cycle easily converted to 2 ATP. The 6 NADH from the Krebs cycle provided us 15 ATP. And the 2 FADH2 from the Krebs cycle gave us 3. Adding these up, once again, we have our 32. Now let's look at ATP production from 1 molecule of fat, or palmitate. So palmitate is a 16-carbon saturated fatty acid. And once again, it's going to take 2 ATP to activate palmitate. We have to determine or calculate the rounds of beta oxidation that occur. And how we do that is we take N divided by 2 and subtract 1. N is the number of carbons, so we have 16 carbons. We're going to divide that by 2 and then subtract 1. That gives us 7 rounds of beta oxidation, which occurs within the mitochondria. And for each round of beta oxidation, we end up yielding 1 NADH, 1 FADH2, and 1 acetyl-CoA. Remember, the NADH and FADH2 are reduced enzymes. So out of 1 palmitate, we end up with 7 NADH, 7 FADH2, and 8 acetyl-CoA. The acetyl-CoA will make their way to the citric acid cycle, or Krebs cycle, once again. And as they do so, for every acetyl-CoA that enters the citric acid cycle, we're going to get 3 NADH, 1 FADH2, and 1 ATP. And we've got to multiply that by the 8 acetyl-CoA. And we do so here on the right-hand side. So the total yield from 8 acetyl-CoA, we have 24 NADH, we have 8 FADH2, and we have our 8 ATP. Our calculations then occur as we add those that were created from the beta oxidation to those created from the citric acid cycle. So 7 plus our 24 gives us 31 NADH total. The 7 FADH2 plus 8 FADH2 gives us 15 total. And in the citric acid cycle, we had 8 ATP created, and we carry those over. Now we need to go into our next step of oxidative phosphorylation. So we take our reduced enzymes and we go through our calculations once again, or conversions once again. So 2.5 multiplied by 31 NADH provide us 77.5 ATP. 1.5 multiplied by the 15 FADH2 give us 22.5 ATP. And from the citric acid cycle, we end up with our 8 ATP we've carried down. We add these together, we end up with 108 ATP. But remember, once again, it took 2 ATP to activate palmitate. So we subtract those two and we end up with 106 ATP. How does this apply to the real world? Well, we can see in the chart here, sample effect of intensity and duration on a primary energy system utilized. We can see under very high intensity for 0 to 6 seconds, we're primarily using the ATP, PC, or phosphagen system. As our duration increases and our intensity starts to lower a little bit, we utilize the ATP, PC, and anaerobic glycolytic system, or fast glycolysis system. As our duration increases once again from 30 seconds to 2 minutes, and our intensity goes from moderate to high, we are using the anaerobic glycolytic system, or fast glycolysis. From 2 to 3 minutes at moderate intensity, our anaerobic glycolytic and aerobic system are both utilized, which would be our fast glycolysis and oxidative system. And anything over 3 minutes with lower intensity is typically our aerobic system or oxidative system. And there are factors that affect our energy systems and how they operate. Those obviously include duration, which is mentioned here, intensity, if oxygen is present or not, and the depletion of fuels, particularly food and chemicals, during exercise. So this is a very quick overview of the ATP system and our yields from glycogen and fat. I hope you enjoyed the presentation and appreciate you watching it. My references are listed here on the very last page. Have a great day.